Welcome to this class in the course Mathematical Foundations of Machine Learning. In this class, we will continue with our discussions on the fundamentals of probability theory and relate the ideas of vector valued random variables and joint distributions to the problem of machine learning with examples. Last time, I gave an introduction on why one should look at the problem of machine learning from a probabilistic standpoint. And we also defined some foundational ideas of probability theory, including sample space, event spaces, and the probability measures. And I also introduced you to the idea of random variables and why random variable is needed. And what we work with in practice are realizations of random variables, as they call it. Mathematically speaking, what we have are vectors from the range space or range set of the function called random variable. Okay, that is what we measure from. Okay. And whenever we say that there is a random variable and you have some measurements done, from a probabilistic standpoint, you have to always remember that there always is an underlying sample space that gave rise to this particular random variable, and with a sample space also comes a probability measure which has been pushed forward into being a probability distribution function, okay, which is also called the cumulative distribution function or CDF. So, you have to always remember this. Okay. So, from there now when we defined, I defined the random variable as a scalar valued function, in the sense that you have sample spaces, and from sample spaces, from the elements of sample space, you map them onto real numbers. Now, one can generalize this idea onto vector valued random variables, wherein the range space of this function called random variable is no longer R, but a d dimensional real space. Okay. So, let us define that first. Now, vector valued random variables here, the range set or the codomain set of the random variable of the function. See, note that I have been repeatedly using the word function for random variable because that is what the object is, okay, despite the misnomer. The range set of the random the function called random variable is Rd, which is a d dimensional real space where d is a scalar. Okay, which means that from sample space omega you have the random variable x, that is mapping the sample space to Rd. These are also called the vector valued random variables, where from the sample space you map it onto Rd, okay, with a d dimensional real space. Okay. Now, this can be viewed from two different angles. One as a function or a single random variable that maps your sample space to a d dimensional real space, or one can see this as a collection of d scalar valued random variables. Okay. So, to have that view, let us first define what is called as multiple random variables or joint distributions. I will tell you why this viewpoint is important and how does these two viewpoints converge. Let omega be a sample space corresponding to some random experiment. So, there is one sample space that we have. Okay. So, define two functions. So, call them x1 and x2. Note that I have been using lower cases now for these random variables. I'll tell you why. I am doing this deliberately. I'll tell you why I am doing this. Define two functions x1 and x2, which are x1 is a function from the sample space to R. So, this is one scalar valued random variable, and x2 is another function on the same sample space. Remember that, or rather note the fact that one can define multiple random variables or multiple functions between two pairs of sets always, right. You can define multiple functions between sets, and because you can define multiple functions between sets, there can exist multiple random variables on the same sample space. Okay. Now, corresponding to these, there also exists the respective distribution functions, the corresponding distribution functions. It goes with because the moment you define a sample space, there is a measure, okay, and the moment you define a random variable, there is always a distribution function corresponding to it. So, you have two distribution functions. Okay. Now, recall that in the set theoretical view for probability theory, we can define the probability over set operations of events. Now, what do I mean by that? If there exist two events A and B, you can define, and they have probabilities corresponding to them, right, the measures corresponding to them. We saw by definition this probability measure can also accommodate the unions and intersections of these events. So, we can define probability of unions and probability of intersections and so on. So, which means that if you define two random variables, okay, because they by definition their inverse images always map back to some element in the event space F, and because you can, since you can talk of intersections and unions in the event space, there should be a way to combine these random variables. Does that make sense? Right. So, that is exactly what the idea of joint distributions are. Okay. So, define joint probability distributions as, so now P x1 x2, okay. Now, you evaluate this at 2 points, correct, evaluate this at yeah, for the lack of notation I will have to write as A and B. Let us say that you evaluate at 2 points A and B. What is this given as? This by definition, this is the probability, this is the measure, okay, that corresponds to an event E, which is the inverse image of the Cartesian products I should say that it is the event that corresponds to the intersection of so let us say that E is the event which is the intersection of inverse images of under x1 and x2 respectively. Make sense? So, there are two random variables that we are talking about. and inverse images of both of them correspond to some events in the original sample space. Take the intersection of both of them and you get another event. The probability measure corresponding to that particular event is what is defined as the joint distribution. Okay, make sense? Now you can extend this idea to n random variables. So, it need not be 2 random variables, you can extend this idea into n random variables, in which case, so you have a joint distribution between n random variables or d random variables that are all defined on the same sample space, right. So, that is exactly what the idea is. So, now this, the above idea can be extended to d scalar random variables extended to d number of scalar random variables. Okay. Now remember that we also said that there can exist vector valued random variables, where the function which is the random variable maps from the sample space to a d dimensional real space, right. Since we can define d number of scalar valued random variables, there seems to be a connection between these two. Turns out that they are exactly the same. Okay. So, a vector valued random variable can be seen as a collection of d scalar valued random variables that are all defined on the same sample space. Okay. That is what the idea is. So, for the rest of the course, without the loss of generality, I assume that we are working with a d dimensional vector valued random variable. So, when I say that there exists a d dimensional vector valued random variable, you should know what is happening. So, either you can see that as one function from the sample space to Rd with the corresponding vector valued with the corresponding underlying distribution. Okay. See, if it is a d dimensional vector valued random variable, then the interval that we see here happens to be the Cartesian product, and we just saw that the last time, right. It is the Cartesian product, or if you want to go back to the sample space, it is, you can see that as the intersection of all the events corresponding to the individual scalar valued random variables that could be seen as defining d different functions on the same sample space. Okay. Okay. On top of it, right, once you define multiple random variables on the same sample space, you can define things like conditional distributions. Since there exist conditional probabilities, I told you the last class, right, whatever applies from the set theoretic point viewpoint of for the probability theory can be extended to something in the space that is put forward by a random variable, a function called random variable, right. So, now define conditional probabilities and conditional distributions corresponding distributions if A and B are two events corresponding to a sample space, then we all know that you can define what is called as probability of the event A conditioned on B as the probability of the intersection of these two events with respect to the probability of the conditioned event. So, this is the definition of the conditional probability. And what does this correspond to? I mean, if you want to interpret, given that the event B has already occurred, evidenced by something, what is the likelihood or the probability that the event A occurs? That is the way to interpret it. Okay. Now, since everything that we do from the set theoretical angle can be translated to in distributions, you can define what are called as conditional distributions. Okay. So, we define conditional distributions as P, suppose x and y are two random variables defined on the same sample space. See, please note that here x and y are generalized in the sense that they can both be vector valued random variables. Okay, from now on, whenever I say that I am dealing with a random variable, I always mean that I am talking about a d-dimensional vector valued random variable where the function is from omega to Rd, remember that. Okay, so there are two random variables, and by the way the range space of these two may be different in the sense that one can be Rd, one can be Rk, does not matter, you still just have two vector valued random variables. You can define the conditional distribution P of x given y. So, evaluate that at x, at some x, okay, it evaluates at some x given y is fixed to some value y. So, always remember that when we define the conditional distribution, the conditioning random variable is fixed at a value, okay, and that is why the conditional distribution is always said to be a function of the conditioned random variable, because once you fix it, the sample space get shrunken, okay, and you fix that and then define a distribution over it. So, always see from now on whenever I write, so I do not write this y equal to y from now on, I will just write P of x given y, but when I write that always remember that the conditioned random variable is fixed to a value, a given value. Given that this is fixed to a particular value, the question that we are asking is what is the underlying distribution. So, how is this defined? So, this is defined as the joint distribution divided by what is called as the marginal distribution. So, this is called the marginal distribution because by definition if x and y are two random variables, and please note that I am assuming that the underlying random variables are continuous when I write this definition, okay, two random variables. So, marginal of x is defined as assuming that this integral is well defined. So, by the way, does anybody know why this is called a marginal distribution? It is pretty interesting. Suppose these two are discrete random variables. Discrete random variables can be written as a table. The joint distribution of a discrete random variable can be expressed as a table, right. Now, if you look at evaluate the margins along the margins of that table, whatever you get is the marginal distribution for all of those x's. So, that is why it is called the marginal distribution, right. It is literally the margin, the one that gets evaluated at the margin. So, basically what we are saying is that if there are two random variables that are defined on the same sample space, if I integrate out one of the random variables, or rather I would nullify the effect of one of the random variables by adding all the values corresponding to the other random variable can take, I will get the behavior of only one of the random variables, and that is what is called as the marginal. Okay. Now, we know what joint distributions are, now we know what marginal distributions are and what vector valued random variables are. Okay. Again, as I said, this is a very quick primer on the probability theory and the notions that we need for this particular course. I am assuming that all of you have done this course rigorously. This is just refreshing your memory. Okay, this is not a full probability theory course by any imagination. Okay, so now we know. So similarly, you can define the marginal on y as well. So marginal on y can also be defined as you take the joint distribution and you integrate out x. And by the way, when I write this integral y integral x, this is not a one dimensional integral, right. Depending upon what the range space of this random variable is, you will have to, if it is let us say R3, you are talking about triple integrals, and if it is RD, it is a d dimensional integral and so on. So, for notation I am just writing it as integrating over x, okay, which is, in fact this is sort of abuse of notation when I say that, see, this y denotes a function, okay. You cannot integrate over a function, you can integrate over sets. So, by this I mean that this is the, I mean, the range of y, that is what I mean. I mean, to be precise, it is, maybe we will write that, no, this is
these are capital X and Y, right?
come again,
These are capital X and capital Y.
capital X and capital, because they are functions, but the integration is being done over the range of x and range of y when you compute the marginals, okay. Right, now comes the interesting part. Now, you remember our problem, right. Initially our problem was that we have an X-ray and we wanted to know whether that X-ray corresponds to the disease case or non-disease case, and how are all these related to this, okay. Okay, so now let us try to get that example grounded in these under with these notations and languages. Yeah, I will do that and then we will go to the density functions. Okay, we will see in the next lecture.